Welcome to the 10th session on galvanic cells. In this session, we will be dealing with the liquid junction potential, LJP is the abbreviation for that. This liquid junction potential is seen in those electrolyte concentration cells in which the electrolytes are in direct contact with each other. Okay, so let us move on to the topic. So, suppose we consider two cells in which there is a partition which is porous and we have two electrodes inserted in the electrolyte solution. In the first case, let the concentration or activity be represented as A1 and in the other case, let that be A2. We know that when two solutions of different concentrations are put together, natural tendency of the electrolytes to move from higher concentration to lower concentration, it exists as such. In addition to that, we will be having the movement of ions, where the movement of ions takes place under the influence of the potential developed in the cell. Okay. So, we are going to consider what are the factors that are taking part to cause the liquid junction potential when the two electrolytes of two different concentrations are in direct contact. Okay. So, in a cell with transference, where two salt solutions are of different concentrations in direct contact with each other, a potential will be set up at the junction of the two solutions. There will be a potential developed and as a result of this, this potential makes a contribution towards the cell potential. Okay. So, liquid junction potential can be defined as in cells with transference, when the two salt solutions are in direct contact with each other, okay, there will be a potential developed at the junction of the two solutions, which makes its own contribution towards the EMF of the cell. To the EMF of the cell, it makes some contribution. It can be a positive contribution or a negative contribution. And this potential is known as liquid junction potential. And why does this liquid junction potential arise? This is just because there is a difference in rate of diffusion of the two ions moving across the boundary. That is, some of the ions may be moving faster, the other ions may be moving at a slower speed, and this makes to develop a potential at the junction of the two liquids. Now, I will go into detail. Suppose you are having a anodic solution, let this be a concentration cell, let these two be the electrodes dipped in it and these are the electrolytes, whatever be the electrolyte, let this be the anodic compartment and this the cathodic compartment. And this the cathodic compartment. Okay. Now, in a cell at anode, we know that oxidation takes place. Oxidation means that is the removal of electrons, and as a result of oxidation at anode, what will happen? There will be, as a result of oxidation, results in the production of cations. Okay. So, at anode there will be an excess of cations formed due to the oxidation taking place at the anode. Now, at the cathode, we know the reduction is occurring and there will be accumulation of anions in the, you can't say anions, you can say rather say anions will be coming from the electrolyte or you can rather call it as reduction in concentration of cations. Here cations are increasing, while in the case there will be the concentration decreases in the case of cation. Now, what happens is that when there is an increase in concentration of cations at one side and on other side there is a decrease in concentration of the cations, naturally these ions tend to flow from one half cell to the other half cell. Okay. Now, what happens here is, that is, suppose I am taking HCl as the electrolyte. Okay. From anode, HCl has got a tendency to flow to the cathodic solution. At the same time, chloride ions have a tendency to move towards the anodic solution. Now, what happens here is, this is what happens in the electrode reaction. Okay. Now, remember, these are electrolyte concentration cells where electrolytes are in direct contact. So, there is a natural tendency for the higher concentration, that is, if HCl has got higher concentration here, suppose here we have the concentration to be higher. Okay. HCl concentration is higher on this side, and then this HCl has got a natural tendency to move from a higher concentrated solution to a lower concentrated solution, that occurs. Now, what happens is, when HCl tries to move, there are two ions moving, the H plus ions and Cl minus ions. Okay. Now, these two ions, their velocities or speeds may not be same, and usually it is observed that H plus ions move faster than chloride ions. Now, what happens is, when HCl from a higher concentration is migrating to the lower concentration, since H plus ions move faster, they get accumulated in the dilute solution. So, at dilute solution, what will happen? There will be an accumulation of H plus ions, because chloride ions are following it, and if 10 H plus ions has reached in the lower concentration or dilute solution, chloride ions may be some 4 or 5 have reached over there. So, the net result is the dilute solution will become positively charged, because more of H plus ions reaches at the dilute solution. And what happens is that the more concentrated solution, since all the chloride ions as how much the H plus has migrated, need not have been transferred to the dilute solution. So, the chloride ions remaining in the concentrated solution will have a positive charge for that solution. It imparts a positive charge to that solution. So, concentrated solution will have a charge of that ion that moves slowly, while in dilute solution it will have a charge of that ion which moves faster. So, what happens is, these two solutions will be at two different charges, or you can say that when these the region where these two solutions meet, there will be a potential developed, because they are oppositely charged. The two solutions are oppositely charged and a potential is developed at the junction of these two liquids. Now, what happens is, this represents the liquid junction potential, and the reason for that is because the H plus ions and chloride ions, they do not move with the same speed. H plus moves faster, while chloride ions at a slower rate. So, the concentrated solution will have more of chloride ions, and therefore, that will be negatively charged, and the dilute solution where more of H plus ions has been arrived, because they are moving faster, that will be having a positive charge. Okay. So, that is what is mentioned here. The H plus ions and chloride ions will migrate from a concentrated solution to the dilute solution, but H plus ions move faster than chloride ions, resulting in the accumulation of H plus ions in the dilute solution, and therefore, the dilute solution will be positively charged, and that of chloride ions is concentrated solution that will be negatively charged, because they go slowly. So, you will have more of chloride ions in the concentrated solution. This results in the potential difference, and this is how a liquid junction potential originates in cells with transference. Okay. Now, this can be eliminated by two methods. One is if we have an electrolyte in which cations as well as anions, they move with the same speed. So, if 10 cations has arrived in the concentrated solution, naturally the anions also 10 of them will be arriving along with the cations. So, there will not be any charge separation for these two solutions. Okay, that is one way. Another way is you do not keep these two solutions in direct contact, only then the liquid junction potential arises. So, keep them apart, and usually what we do is we use a salt bridge for an indirect contact between these two cells. Now, this is what we say, that is liquid junction potential can be eliminated if the cell is without transference. Okay. Or you can have it both ways, that is you are having either solutions of same cation and anion speeds, or you are going to keep it without transference, that is using a salt bridge. Now, if cell with transference has got liquid junction potential and cell without transference does not have liquid junction potential. So, what happens is you take the difference of potential of these two cells will give you the measure of liquid junction potential, provided it is the same cell. Suppose I am taking a hydrogen concentration cell with transference. You will have to perform the same cell with the help of a salt bridge, so that it will be without transference. The same cell should be with transference and without transference, and you take the difference of these two potentials, you will get the value of liquid junction potential. Okay. Now, let us see some of the cells and how a liquid junction potential is to be calculated. Now, we are going to consider the concentration cell in which the electrodes are reversible with respect to cation. So, first case is we are taking cells with electrodes reversible with respect to cations. Now, the Nernst equation for cell without transference, which we have seen in the previous sessions, is equal to 2.303 RT by NF log mean ionic activity of 2, solution 2 divided by mean ionic activity of solution 1, okay, while with the transference, that is ET is equal to 2T minus. Just remember, note the point, that is T minus is the transference number of anion when we have a cell with electrodes reversible with respect to cation. Okay. So, 2T minus 2.303 RT by NF log mean ionic activity of 2 divided by mean ionic activity of 1. So, these are the two expressions for cell without transference and with transference. Now, what we are going to do is, to get the liquid junction potential, you will have to subtract the values, that is ELJP, that is liquid junction potential, is equal to cell EMF of the cell with transference minus EMF of the cell without transference. Now, let us substitute the values and find out the value. Okay. So, E with transference is 2T minus 2.303 RT by NF log mean ionic activity of 2 divided by mean ionic activity of 1. That represents E with transference. Okay. So, this is E with transference, and E without transference is, you do not have the 2T minus, it will be 2.303 RT by NF log mean ionic activity of 2 divided by mean ionic activity of 1. One more point, that is R is the universal gas constant, T is the temperature in Kelvin scale, N is the number of electrons involved in the electron reaction, and F represents the Faraday, which is equal to 96,500 coulombs. Okay. Now, we know that here we have 2T minus, and here we do not have anything else, that is, you can consider that as 1. the common factor 2.303 RT by NF log mean ionic activity of 2 divided by mean ionic activity of 1. So, I will just show that. See, this is same in both the equations. Sorry. Okay. So, I can take out that as a common factor, and we have ELJP is equal to 2T from this, and here you will consider that as 1. So, 2T minus 1, then the common factor 2.303 RT by NF log mean ionic activity of 2 divided by mean ionic activity of 1. Okay. Now, here we have 2T minus, that is the transference number of anions alone. Now, what we have to do is, we are going to involve both cation and anion, the transport numbers, and therefore, what I am going to do is, we have an expression that is T plus T minus is equal to 1. So, I am going to substitute this for this one. Okay. So, ELJP is equal to 2T minus of, instead of 1 I will put this in square bracket, T plus T minus, that is I am going to substitute that for 1, because 1 is equal to T plus T minus. The rest of the equation as such, 2.303 RT by NF log mean ionic activity of 2 divided by mean ionic activity of 1. Okay. Now, let us solve this. See, this is 2T minus, I will open the bracket, 2T minus T plus minus T minus, again the rest of the equation as such, 2.303 RT by NF log mean ionic activity of 2 divided by mean ionic activity of 1 whole in log. See, this is 2T minus and minus T minus makes it 2 minus 1, 1. So, this becomes T minus T plus, and the rest of the equation as such, 2.303 RT by NF log mean ionic activity of 2 divided by mean ionic activity of 1. Okay. So, that is the expression ELJP is equal to T minus T plus 2.303 RT by NF log mean ionic activity of 2 divided by mean ionic activity of 1. Now, one more point to be clarified, that is T minus T plus. If this is to be positive, what should be there? T minus should be greater than T plus. If T minus is greater than T plus, the liquid junction potential is positive. What does it mean? Liquid junction potential adds to the EMF of the cell. Positive means. Okay. Now, you can take the other case. So, it becomes positive when this is T minus is greater than T plus. I will make it like that. Then, if T minus is less than T plus, what will be the condition? It will be negative. That means that EMF makes a negative contribution to the cell potential. So, you will have a lower cell potential measured rather than the theoretically or expected value of the potential of the cell. Okay. Now, what will happen when these two are equal? The value will be 0, no liquid junction potential. So, there is a condition I told just to eliminate the liquid junction potential, you can have the transference numbers of cation and anion same. How much current, fraction of the current has been carried by cation or the anion, if they are same, or you can say they are directly proportional, the current carried is directly proportional to their velocities or the speed of that. If the speed of the cation and anion are same, which means that their transference numbers or transport numbers will be same, and therefore, in such cases you won't find liquid junction potential at all. So, these conditions are mentioned here. See, if T minus is greater than T plus, ELJP will be positive, and the liquid junction potential makes a positive contribution to the cell EMF. It gets add up to the EMF of the cell. So, it will be a greater value than normally expected value. Next is, if T minus is less than T plus, ELJP is equal to negative, or liquid junction potential makes a negative contribution to the cell EMF, or you can say that cell EMF measured will be less. Okay. When these two are equal, ELJP is equal to 0, you won't have any liquid junction potential. Okay. Now, let us consider the concentration cell. Now, one more point to be stressed is, when I have a cell reversible with respect to cation, this was a cell reversible with respect to cation, just focus on the point, it is transference number of anion minus transference number of cation. Okay. So, when I am having reversible with respect to cation, it is the transference number of anion minus transference number of cation. Now, we are moving to the other type, that is, these are cells in which the electrodes are reversible with respect to anions. Usually, a metal in contact with metal insoluble salt which contains a solution having an anion in common. Such electrodes are reversible with respect to anions. In that case, the EMF of the cell without transference is equal to 2.303 RT by NF log mean ionic activity of 1 divided by 2. In the other case, it was 2 divided by 1. Okay. Then E with transference, when it is anion, please note that here it is T plus, in the other case it was T minus, and this is with respect to anion, just opposite in charge. Okay. 2T plus 2.303 RT by NF log mean ionic activity of 1 divided by mean ionic activity of 2. Now, as said before, the liquid junction potential is equal to E with transference minus E without transference. Okay, I will substitute that. That is 2T plus 2.303 RT by NF log ionic activity, mean ionic activity of 1 divided by mean ionic activity of 2 minus, and that represents without transference, you do not have the 2T plus 2.303 RT by NF log mean ionic activity of 1 divided by mean ionic activity of 2. Okay. Now, taking the common term 2.303 RT log mean ionic activity of 1 divided by mean ionic activity of 2 in both cases, you have 2T plus minus 1 common factor 2.303 RT by NF log mean ionic activity of 1 divided by mean ionic activity of 2. Now, again we are going to substitute, that is T plus T minus is equal to 1. So, I am going to substitute this for 1 as T plus and T minus. So, ELJP is equal to square bracket 2T plus minus T plus T minus. Okay. The rest is 2.303 RT by NF log mean ionic activity of 1 divided by mean ionic activity of 2. The whole thing in log. Okay. Here it is 2T plus, and this minus gets inside, this becomes minus, and here we will have only 1T plus. So, this will be solving, I will open the bracket, 2T plus minus T minus minus T minus. Oh, sorry, this is T plus. See, 2T plus, and this becomes minus T plus, you will have 1T plus 2.303 RT by NF log mean ionic activity of 1 divided by mean ionic activity of 2. Okay. So, here by subtracting you will get it as T plus minus T minus into 2.303 RT by NF log mean ionic activity of 1 divided by mean ionic activity of 2. Okay. Just like in the similar case, we have T plus greater than T minus, where ELJP is positive and LJP makes a positive contribution. T plus is less than T minus, it becomes negative, it makes a negative contribution, and when they are equal, there is no liquid junction potential. Now, how can a liquid junction potential be eliminated? Liquid junction potential, it interferes with the exact measurement of the potential of the cell, because this liquid junction potential may add or get subtracted from the value. So, we have to minimize that. For that, there are two options. One, you can have eliminate liquid junction potential by using a salt bridge. The other thing is, you can have two electrolytes where the cations and anions have are the same transport numbers. So, you can eliminate that. And salt bridge, naturally what we use is the solutions like KCl, potassium nitrate, ammonium nitrate, lithium acetate, all those electrolytes are generally taken, in which both have the same transference number, the cation as well as the anion. So, you can use a salt bridge also, which is a very easy method to do it. And advantages of salt bridge is that you can eliminate liquid junction potential, preventing mixing of the two electrolyte solutions. Two factors are there, you can prevent the mixing of electrolyte solutions. Now, next is we have a problem in which the EMF of the cell with transference is an anion reversible cell, where HCl has got activity 0.1751 and in the other case 0.09049, and it is AgCl in contact with HCl solution, and its EMF is 0.0282 volts, and the corresponding cell without transference has got a potential 0.01698 volts. Calculate the liquid junction potential and the transport number of H plus ions. Okay. You are supposed to find the liquid junction potential. So, what we do is, first of all, you will have to find out the value of N in that. We know that in this chloride ion takes up Ag and Ag gets oxidized to Ag plus. So, you require 1 electron. Okay. And therefore, in the other case, this is the reverse of that, where 1 electron will be used up. So, the value of N is equal to 1. There are two methods you can solve this, that is liquid junction potential is just you take the values with transference and without transference and take the difference, and with transference it is 0.02802 volts minus without transference is 0.01698 volts. You subtract these two and you will get the value as 0.01104 as its voltage. This is a liquid junction potential. Now, you can solve for liquid junction potential in two ways, that is liquid junction potential is equal to 2T plus minus 1 2.303 RT by NF log mean ionic activity of 1 divided by mean ionic activity of 2, from which we are going to find out the value of 2T plus, and from that we will get the value of T plus. Liquid junction potential has been substituted. 2T minus is equal to 0.0. The activities are being substituted. Okay, the values. Now, we have taken the solve for this. You get the answer as this, and 2T plus minus 1 will be equal to 0.01104. Okay, taking this to the other side, it comes in the denominator 0.5. Sorry, so zeros are missing, 0.0591 591 into 0.2867. Okay, and finally I will take it as 2T plus is equal to 0.01104 divided by 0.0591 0.2867, and minus 1 comes over here, it becomes plus 1, and T plus will be equal to 0.01104 whole divided by 0.0591 into 0.2867 plus 1, and this should be multiplied by 1 by 2, and you will get the answer as 0.82509. And another easier method for this is, we have the two expressions, that is ET is equal to 2T plus 2.303 RT log mean ionic activity of 1 divided by mean ionic activity of 2. Without transference, it is only difference is it does not have 2T plus. So, if I divide ET by E without transference, the whole thing, these two are same, they get cancelled, and you will get it as 2T plus. It is an easier method, you can follow this. Now, ET without transference is equal to 2T plus, and substituting T plus is equal to 1 by 2 into ET divided by E without transference. The values are given, both the EMF values are given there, that is 0.02802. 0.02808 or 02. Oh, it's 02. Divided by the other value is 0.01698. 0.01698. And in the denominator you will have a 2, and you will get the same answer for T plus as 0.82509. In both cases you are getting the same answer, and therefore, it is better you follow the second method rather than the first method for calculating the transport number. It is very simple. Okay. Now, to conclude, we have been seeing concentration cells with electrodes with respect to anions as well as the cations, both these we have seen, and we have found the expression for electrode with liquid junction potentials, which is equal to 2T minus 1 2.303 RT by NF log mean ionic activity of 2 divided by mean ionic activity of 1, or you can put it as T minus, which is a difference between T minus and T plus, into 2.303 RT by NF log mean ionic activity of 2 divided by mean ionic activity of 1. And this is a case for cation. In the case of anion, you can just watch that in wherever you have a T minus, you will be having a T plus. So, in this case, here in the bracket you will have 2T plus minus 1, and the rest of the equation is same, and here instead of T minus minus T plus, you will have T plus minus T minus. And then we have been dealing with the liquid junction potential and the origin of it and how it can be eliminated. So, that is all for this session. Thank you.